Hi, this is the second part of the video of red-black tree. I'll show you the implementation of red-black tree using C#. So this is just one file, red-black tree. So let's start from the colors. Color is enum, so it's red or black. Remember, double black is not a color. It's a temporary label of the current status of the subtree. Then let's check the tree node. The tree node is just stores a key value pairs where the key must be comparable. We need the key to sort the red-black tree. It contains a key and contains a value. It contains a pointer to its left subtree and a pointer to the right subtree. So all these are the same for all binary search trees. And then in addition to that, it has a color, which is either black or red. Do we want to keep another label for double black? We don't need that. I'll show you where to store the double black. The thing is, double black is a temporary label. If we put double black at here, it will become permanent label, and every node has that label. And some other implementation has another pointer to its parent. It's a back pointer. I don't believe that's really necessary. Actually, having one more pointer will take space. It will reduce the performance, and you have to manage this back pointer. It's point to the wrong place, and everything gets messed up. I don't believe we need a back pointer to the parent. So let's go to the tree. So these are the data of the tree. So it contains a pointer to the root, and here it's a boolean. We show it's double black. We just need a global variable, a global boolean for the instance to show the status of double black. And here we also have a pointer pointing to the node which has been deleted. This is useful for deletion. So it's something like after you delete a node from the tree, you keep a pointer to the node which has been deleted. Then maybe you can do something with this node. Let's start from for this class of tree, you don't need a constructor, because by default this is null. The root node is null, means this is a empty tree. So let's start from static helper method, like this one, get color. So you pass in a node, you return a color. If it's null, it's a black. Otherwise, it just returns the color of this node. Another one is double red. Remember, in the insertion, there may be a double red violation. So the definition of double red is this node is red, and its left child is also red. So this is a double red helper method. Another helper method is left rotation and right rotation. Just use the left rotation as an example. You pass in a node, you return a node after you perform the left rotation. So after you perform the left rotation, you actually return its the root becomes its right child. So you keep a pointer to its right child, and you reconnect the pointers, and you return this pointer pointing to the right child. So this is a left rotation. The same idea is for right rotation. When you do a right rotation, you actually the tree, the root of the subtree becomes the left child. So you keep a pointer to its left child, and reconnect the tree and return this temporary pointer. So also all the rotation, you pass in the tree, and then you return a pointer of the pointing to the new subtree. Now let's go to the public method. Let's start from this search. So you have a get value. So this get value actually calls this helper static method. This helper static method is a recursive method. You pass in the key because you search by the key. You pass in the pointer to the root. So you are searching this key in this subtree. So you know, for the node, it doesn't have back pointer. So the programming pattern is the recursion. Okay, you will see recursive call in many places, including search. So first, if this root, the pointer, if the pointer to the subtree is null, which means this tree is empty. You're searching a key in the empty red-black tree. So C# standard typically throws an exception. So key not found exception. Well, in Java, maybe you return a null. That's just a different implementation. Then if the root is non-null, then we proceed. So we compare the key with the key of the root, because the key is comparable. So we compare that. So if this is equal, which means that's a search hit, we return the value of the root. We find the key already. So otherwise, if the key is less than the key of the root, we go to its left subtree. Otherwise, we go to its right subtree. So you see, this is a recursive call. So this is done. So recursive call lets you write very concise code. So this is just a few lines totally. See, less than 20 lines. So this is a search get value, and here is a method, has key, that works the same way. Has key, you go to this recursive method, you pass in the key, and you pass in a pointer pointing to the root, or to see whether the key exists. It works the same way as search. So search is the same for all binary search trees, including regular binary search trees and AVL tree. That's another type of auto-balanced self-search, auto-balanced binary search tree. Then let's go to add. So that's insertion. You insert a key value to this red-black tree. So you need to search key value pairs. So first, what you do is to reset the key into the initial state. So by default, this delete is null and double black is false. You assume this one is you open a session to insert something to the red-black tree. So you reset this state, reset this session. So then you call this method. This method is actually what's doing the work. You pass in the key value and the pointer to the root of the subtree. So in this case, this is the whole tree. And then finally, okay, the last step, after you have added the key value pairs to this root, you set the color of the root to black. This is remember, it's possible after you run this, the root becomes red. So you reset the color to black. So it's always legal to flip a color from red to black. It only increases the black height of this subtree, but in this case, the subtree is the whole tree. So this is the insertion. Let's go to this recursive method. This is the method that's really doing the work. Add to red-black tree recursively. So you pass in the key value and the pointer to the root. So remember, for the insertion of binary search tree, the insertion happens at the leaf. This is the same situation for red-black tree. So if the node equals null, which means you are at the leaf, then you create a new tree and return it. So in this case, you take this key value pairs and a pointer to the root, and you return a pointer of the new subtree after you have inserted. So this is the case. When you add the leaf node, you create a new tree, a new node with the key value, and the color is red because the color of new node is red. You don't want to keep the balance of black height. So this one is null. The node is null, which means you're at the root level. You're at the leaf level. So if the node is not null, then you compare the key with the key of the node. That's a comparison. So if they are equal, which means the key exists already, so what you do is actually update. You update the value, and then you are done. So you return this node because you will return this node because you don't do anything on the tree. You don't do anything else on the tree. You only update the value. You don't do rotations. So you return this node. Otherwise, if the key is less than the key of the node, then you go to its left subtree. So you call this method recursively, but you go to its left subtree. So still passing the key value pairs, and then the pointer becomes its left subtree. So after you finish this one, after this recursive recursive call finishes, you modify the left subtree. So when you modify the left subtree, you may cause the double red violation. Remember, after this statement, the right subtree is untouched, so you don't need to worry about right red violation. You only need to consider double red violation because only the left subtree is modified. Then you check whether the left node is double red. If it's not, then you don't need to do anything. You just return this node. If it is, you need to do a rotation. You do a right rotation of the current node, and you update the current node to the after you perform the right rotation. Then you need to flip the color. This color becomes black. And this node's color should be red. Then that means the violation may propagate upwards. It may propagate upwards. So in this case, this is the key is less than the key of the node. If it does propagate all the way to the root, remember the last step is to reset the root color to black, so it won't cause any violation. Then if it's greater, the key is greater than the key of the node, we go to its right subtree. So we call this method recursively the same key value, but we go to its right subtree. And after this returns, the right subtree is modified, and the left subtree is not modified. So you need to worry about the right red violation. You only need to check the color of the right node. If it's red, then there is a right red violation. If it's not, if it's black, it's not red, then we don't need to do anything. We just return this node. So now, if there is a right red violation, then we need to consider two situations. If the left node, left child is red. If the left child is red, it means both left and right are red. So you need to flip the color. Both child nodes becomes black, and this color becomes red. The node color becomes red. And if its left child is not red, we need to do a left rotation of the current node, and then we flip the color. We also need to swap this color, so we record the original color of the original root. So we swap the color actually. So in this situation, it may cause a double red violation. But remember, this violation will be resolved in this node's parent. So we are actually done with the insertion. So let's go to deletion. That's a complicated step. So this method is remove. We remove a key. Remove a node containing this key. Remove a node whose key equals this key. So first, we also reset this the red-black tree. Default deleted this default, which is null. Then by default, the double black is false. And then we call this method. It's also a recursive method. We pass in the key and the pointer to the root. And after we call this after this finishes means this key, the node containing this key, has been deleted from this root. And if this root is not empty, which means it's not null, which is not empty, we set the color to black. And then we reset this double black to false, because this function may modify the double black. So we reset the false. So let's go to this method. This is the method is actually doing the work. So this is a delete from red black tree. You pass in a key, and then you pass in a pointer of the subtree from where you want this key to be deleted, and then you return a new pointer of the new subtree in which this key has been deleted. So again, if the root is null, which means the tree is empty, you are deleting a key in the empty tree. So the key does not exist in the tree. It's a search miss. You do nothing. So you return null or you return root. That's the same thing. Then the root is not null. You compare the key with the key of the root. Do the comparison. And then we'll return something. This is the node we are going to return. We just set a pointer. If it equals, that's a search hit, which means you find the node which should be deleted. So remember, when you delete a node from the binary search tree, if the node is a leaf node or it contains only one child, that's easy. So this is just to handle this situation. So deleted means it's a pointer to the node which is deleted, and whether it's double black, well, that's a tricky part. Whether it's double black depending on the color of the root which is deleted, because this node is gone, and it will be replaced by null node or its only child. So this means if the left is null, we go to return its right. If it's not null, then we return its left, because remember, it's leaf or it has only one child. So this code will work. If we delete a black node, which means the black height is reduced by 1, so the double black is true. If the node is red, which means you get rid of a red node, the black height stays the same, so the double black is false. So this is an easy situation. Its leaf has only one child. So what if it has two children? That's a bit complicated. Okay, and let's go over here, because after you delete, you just disconnect the pointer which has been deleted. So such as it's just a standalone pointer. It just point to this node which is deleted. So in this case, this node has two children. What we do is we delete the minimum of its right subtree. Now we have this method, delete minimum of right subtree. Another option is delete the maximum of the left subtree. So the idea is you replace this node with its predecessor or its successor. So in this case, I choose to replace this node with the successor. So let's go to this method. What this method does is to delete the minimum of this original subtree, and we return the new subtree. And also the deleted minimum is stored in this deleted pointer. So this one is a deleted pointer. This is the minimum of the original right subtree. And then we replace this minimum. We replace this node with this minimum, which is this, and reconnect the left subtree and right subtree to this new deleted minimum, the new root. And also we set the color of the new root to its original color. And then after that, it's just a regular deletion. But the deletion may cause the black height of this node of the right subtree to be reduced by 1. So in this case, this may be red double black, and then we need to call this method to resolve the double black. This method takes a parent node and the child node, in which the child node may be double black, and we return a new. We do a tree rotation, color flipping, and return a new return a pointer to the new subtree with the double black resolved. So let's go to this method first, delete minimum. So delete minimum, you pass in a pointer to the node. So it's also a recursive call. So you pass in a pointer, you return a pointer. So if the pointer's left child is null, which means this node is the minimum, you reach the minimum already. So you use a deleted global pointer to point to this node and return its right child. And this double black depends on the color of this node. So this is you because the minimum you keep going the left. So unless there is no left, means you reach the minimum. And here is if the left minimum is not null, so you should call this method recursively. Go to its left child. And then after you have this one deleted, you need to call the resolve double black. And the pointer is parent pointer is node, and its child pointer is left child. Then after you resolve the double black, you return the pointer to the new tree. And let's come back here. In this case, it's a search hit. You find the pointer. You find the pointer to the node which should be deleted. If you didn't find it yet, so you compare the key with the key of the root. In this case, the key of the root is less than the key of the key you passed in is less than the key of the root. You go to the root's left subtree. You call this method recursively, but you go to the left subtree, and then you may call double black for the left subtree. So you call this method again to resolve the double black. In the same situation, if you go to the right subtree, in this case the key you pass in is greater than the key of the root. You go to the right subtree, you also need to resolve double black. And finally you return the root with the double black resolved. So let's go to this method, resolve double black. This is the most complicated function. So this method is exactly the same way as I described in the previous video, how to resolve the double black. It takes a node, a pointer to the parent, and takes a pointer to the child, and the child may be double black. So first, remember the double black may propagate upwards or may stop propagation upwards. If it's not double black, because originally it may be double black, and after propagation it may be not double black. So which means we don't need to do anything. If it's not double black, we just return the parent node. And then here's the situation, the easiest situation. If the child is double black and the color is red, it's red and double black, we just flip the color. The color of the child becomes black, and it's no longer the double black. Return the parent. We don't need to do tree rotation, because double black means the black height is reduced by 1. So in here you add one more black node, so the black height is increased by 1. So double black, the balance of the black height is restored, so it's no longer double black. So this is the easiest situation. So, but what if it's black and double black? Well, in that situation, we have to check the double black is from left or is from right. So in this case, the double black is from left. So if that's the situation, we also need to check another condition, which is the color of the right left. In this one, we have to check the color of the left subtree of the parent's right subtree. Okay, this one we check the color. If this color is black, we just flip the color and then we return a node. Whether it's double black depends on the original color of the parent, so we don't need to do tree rotation. But if this color is red, then we have to do the tree rotation. And this is the same as described in the previous video. Yeah. So and then it's no longer double black. In this case, the double black is from left. So what if it's come from the right? So if double black is from the right, we first have to consider the color of the parent node. So if the parent node is red, we have to do additional check of the color of this left. If this color is red, we have to do a tree rotation, and it's no longer double black. It's a tree rotation and the color flipping is no longer double black. And if this color is black, we go here. In this case, we don't need to tree rotation. We only need to flip the color, and then it's no longer double black. So in this situation, the color of the parent is red. And what if the color of parent is black? So we still need to check the parent's left color, the color of the parent's left child. And if the color of the parent's left child is black, so we still need to check this color, the parent's left. If this color is black, we just need to do a color flipping, and it's double black, because we flip a red node to flip a black node to a red node. We reduce the black height by 1, but we don't need to do tree rotation. It's still a double black. If this color is red, then we need to do a tree rotation and a color flipping, and it's no longer double black. And if the parent's left color is red, we go to this branch. We go here. So we do a right rotation of the parent, and we do the color flipping. Remember, we flip a color from black to red, and then this may cause double red violation. Well, if it doesn't cause double red violation, so we are good. We just it's no longer double black and return the node. If this one does cause double red violation, we have to do further tree rotations and color flipping, and to resolve the double red violation, and then finally return the node. So all of these is exactly the same as I described in the previous video. So you see, we covered all the possible situations exhaustively. So we exhaust all situations. So with the double black will be resolved. So the whole method looks complicated, but it's not that complicated. See, it's just less than 90 lines of code. It's not bad for a method. And this is in C# standard. So like this one takes a whole line. So you write in Java standard, Java code style, this will be shorter. So okay, so this is done for the source code of red-black tree. So in comparison with another type of self-balanced binary search tree, which is AVL tree, I will also attach this node, this code. I'll also upload this code. You can check this code yourself. The AVL tree is more complicated than the red-black tree. You see, it has I think almost 100 lines more than this red-black tree. I didn't realize that the AVL tree is more complicated until I implemented it myself. The reason is AVL tree, you have to handle 3 branches. The left tree and the right tree have the equal height, or left tree is taller, right tree is taller. You have 3 branches to handle. But red-black tree, you have just 2 branches, black and red. And we also require the red node to be left leaning. That will simplify situation. So you can check this implementation yourself for the AVL tree. So I think that's all for this video. Thank you for watching. Bye bye.